Welcome to the deep dive. Today, we're really taking a structured approach to the nuances of Azure networking.
hmm
We're not just going to be defining components like VNets or private endpoints. We're going to dig into the high-stakes scenarios that, determine whether an entire Azure architecture actually works or fails.
That's exactly right. Our focus today is all about application. It's about the crucial and honestly, often counterintuitive ways these networking components interact with each other.
Right.
The source material we're working from is just a fantastic collection of 15 scenarios. Each one is explicitly designed to isolate a common trap, or a wrong assumption people make.
The kind of things you see in production environments.
In production and critically on the AZ-104 certification exam.
Okay, so our mission here is to move you beyond just knowing the definitions. We want you to get comfortable with the practical architecture. We really want to understand the logic behind why certain configuration mistakes are so tempting and how to spot them when you're under pressure.
Yeah, and we're going to spend a good amount of time analyzing things like routing precedence, this idea that you could add one simple rule that just totally black holes traffic to Azure's own core services.
Wow.
We'll also cover the fundamental rules of peering, like why overlapping address spaces are an instant, non-negotiable failure. This is really all about architectural decision-making.
Okay, let's unpack this immediately then. Let's jump right into our first topic, securing the perimeter, isolation, and the critical differences between Azure's two main endpoint mechanisms.
Let's do it.
So we begin with scenario one, which is, I think, the definitive test. Private endpoint versus service endpoint. The situation is really common. We have a virtual machine, a VM, that needs to access a storage account. But the corporate security policy is absolute, zero trust. It requires no reliance on any public IP, and traffic has to be contained entirely within the VNet's private address space.
And the common error here, the trap, is assuming that the service endpoint is good enough.
Right, because it promises to keep traffic on the Microsoft backbone.
Exactly. The Azure literature tells you service endpoints are secure, and that's true, in terms of encryption and avoiding the public internet.
But if the mandate is absolute isolation, why does the service endpoint fail? And why is the correct solution, hands down, the private endpoint?
It all comes down to network identity and the attack surface. So while a service endpoint uses a private source IP from your VNet, the destination identity is still the public IP address of the Azure service in the background.
Okay.
So if you were to look at the whole connectivity flow, the service itself still presents a public interface. Access is just restricted to certain VNet subnets.
So it's like a VIP list for a public club.
That's a great analogy. The private endpoint, on the other hand, flips this entirely. It makes the club completely private.
So by using a private endpoint, what specifically changes about how that service looks on the network?
The private endpoint creates a network interface card, a NNIC, with a private IP address that is sourced directly from your VNet's own address range.
So if my VNet is, say, 10.1.0.016,
Then the private endpoint will consume an IP like 10.1.5.0. The storage account now effectively has a second identity that is purely private and local to your environment. This is the only way to satisfy that zero trust requirement of completely eliminating any dependence on a public service surface.
Now, just to be clear, if the security team mandated disabling all public network access to that storage account, the VMs using service endpoints would just lose connectivity immediately.
Instantly.
But the VMs using private endpoints would keep working because their traffic is all internal.
Precisely. And this leads us to the critical architectural challenge that's noted in the source material, DNS resolution.
It's always DNS.
Always DNS. So if we deploy the private endpoint, our VMs need a way to resolve the storage account's original public host name of blackness storage account.blob.core.windows.net to that new private IP address, the 10.1.5.20.
And if you don't set up the DNS part, what happens?
The VM just defaults to resolving the name using Azure's public DNS, which of course returns the global public IP.
Which you've just blocked at the firewall.
Exactly. So the connection attempt fails instantly. The solution isn't just about the network config, it's DNS. You have to deploy a private DNS zone, usually named something like privatelink.blob.core.windows.net. And this is the crucial part, link that zone to the VNet where your VMs are.
That linkage is what tells the VNet's internal resolver to check the private zone first.
And return the private IP. It's a multi-step process. And, overlooking that DNS step is a classic exam trap.
That dependency really highlights that successful Azure networking needs attention to detail across multiple layers. Let's move to scenario 3. This one deals with network boundaries within a VNet. It's called the subnet isolation myth.
Oh yeah, this is a big one.
Teams often assume that by putting resources into separate subnets, they've automatically created a security partition.
This is a really fundamental concept that gets confused all the time, especially by admins coming from a more traditional networking background. Azure VNets are, by design, fundamentally flat.
Flat, what does that mean exactly?
It means subnets are really just organizational tools. They help with addressing, with CIDR ranges, but they provide zero inherent security isolation. By default, all traffic from subnet A is allowed to reach subnet B, no questions asked.
So if the rule is subnet boundaries are porous, what's the mandatory tool we have to use to enforce those security boundaries?
Network security groups, NSGs. The NSG is your stateful Layer 4 firewalling mechanism. You have to explicitly apply NSGs to control the traffic flow between subnets, treating that subnet boundary as if it were a real trust boundary.
So you define a rule on subnet B's NSG that says only allow traffic from subnet A on port 443, and then just let the implicit deny all rule block everything else.
That's the one.
Okay, let's talk about placement. The source material mentions you can apply an NSG at the subnet level or at the NIC level. When would an architect choose one over the other?
The general best practice, the default approach, is to apply the NSG at the subnet level. It enforces a consistent, broad policy across every single thing you deploy into that subnet. It's great for simplifying management.
So when would you use the NIC level?
You reserve applying it at the NIC level for like microsegmentation or for specific exceptions. Maybe you have a single management VM in a subnet that needs unique permissions that conflict with the general subnet policy.
And if those are applied and the rules conflict?
Azure enforces a composite rule set, and critically, the most restrictive rule always wins for any given traffic flow.
That sounds like a common test point.
It is. If the subnet NSG denies port 80, but the NIC NSG allows port 80, the traffic is denied. End of story.
Now, let's circle back to endpoints. Scenario 12 reinforces why service endpoints are often not enough under strict security mandates. So if we disable public access for, say, an Azure Key Vault, the VMs using a previously configured service endpoint just lose their connection.
Right. The assumption was that the service endpoint was like a permanent access pass.
But it's not.
It's a failure to understand precedence. The service endpoint is basically a signal to the Azure Services public firewall that says, hey, allow source IPs from this VNet. But if you, as the administrator, go into the Key Vault's access policies and set the global default to deny all public network access,
You've overwritten it.
you've overridden the service endpoint's effect. You have essentially just shut the door that the service endpoint was trying to knock on.
So if that global public access is disabled, what two mechanisms still allow connectivity?
You have two paths. The clean, modern path that requires zero public exposure is the private endpoint. That brings us back to scenario 1.
And the other path?
The older path, which still uses the underlying public service, is to explicitly go into the service's firewall, the Key Vault's firewall in this case, and select the specific VNet and subnet you want to allow.
The source material suggests service endpoints are increasingly seen as a legacy solution for highly sensitive workloads. Why that architectural shift?
They are excellent for traffic optimization and for using the Microsoft backbone, but they don't provide that critical defense in depth that you get with true private addressing. When you deploy a private endpoint, you remove the public interface entirely.
Whereas with a service endpoint, it's still there.
The public interface still exists, and you're just relying on the service's internal firewall to filter traffic based on source VNet tags. That can get really complex to manage at scale. Private endpoints simplify the security model by making the resource feel like it's locally addressed.
Okay, let's transition now to VNet peering. This is the cornerstone of building complex multi-VNet architectures, especially that popular hub-spoke model. This section feels like it's full of pitfalls.
It is. The rules for peering are often very different from traditional data center routing. We have to start with the most brutal, non-negotiable failure, which is scenario 4. Attempting to peer two VNets with overlapping CIDR ranges.
The configuration just fails instantly.
Instantly. It's a deal breaker.
Why is that? Why can't Azure handle something like network address translation or NAT to route between networks that share address space, like we might do on-prem?
Because Azure peering is architected to be a transparent, high-speed, logical connection. The goal is for resources in VNet A to see resources in VNet B as if they were locally connected.
Okay.
For this to work, Azure's internal routing system has to be able to insert a clear, unambiguous route for the entire destination VNet CIDR block. When the CIDR range is like 10 overlap, Azure loses the ability to determine the correct traffic direction. It can't distinguish between a local destination and a remote one with the same IT.
So because peering is purely at the IP level, without the complexity of NAT, any overlap creates a fatal routing ambiguity.
Exactly. And the consequence in the real world is often severe. The only solution is to modify the address range of one of the VNets. And depending on how many resources are deployed, this often means deleting and recreating subnets, maybe the VNet itself. We're talking substantial downtime.
This is where upfront planning is everything.
Paramount.
I actually remember a specific incident where an architect had let two different regional teams use the default VNet template, and they both used the 10.0.0.016 range.
Oh, no.
Yeah. The entire global peering initiative stalled for 2 weeks because they had to meticulously migrate one whole region to a new address space.
That is the architectural lesson right there. Especially in hub-spoke, the central hub team has to rigorously maintain a clear IP address allocation scheme. Every single spoke VNet has to be assigned a non-overlapping CIDR range from day one. If you fail there, you fail at the foundation.
So once we successfully establish peering, we run into scenario 10, the non-transitive rule. VNet A is peered to the hub, VNet B is peered to the hub. We naturally expect VNet A to be able to talk to VNet B through that shared hub.
And that expectation is wrong.
Why doesn't that hold true in Azure?
This is the non-transitive nature of peering. Peering is a direct point-to-point relationship. VNet A is only aware of the route it has to the hub. It has no system route that tells it how to get to VNet B, even though B is also connected to the hub.
It's like a chain. A is connected to C, and B is connected to C, but A and B aren't connected to each other.
Exactly, and C doesn't automatically act as a router for them.
So if the default system routes don't enable the spokes to talk to each other, how do we force this transitivity? What's the fix?
We have to introduce a layer 3 routing device into the hub VNet and then configure user-defined routes, UDRs, on the spokes to point to that device.
And what kind of device are we talking about?
The preferred modern options are an Azure firewall or a network virtual appliance, an NVA. That NVA, which is just a term for third-party virtual routers or security devices, acts as the central traffic director.
Okay, walk us through the configuration. How does the firewall actually enable the spokes to talk?
First, you deploy the Azure firewall into the hub VNet. Second, in both VNet A and VNet B, you create a UDR that says something like, to reach any IP address outside this VNet, the next hop should be the private IP address of the Azure firewall. The firewall then receives the traffic, inspects it based on its rules, and uses its own routing logic to forward it to the correct destination VNet.
So the key answer for the exam is, if spokes need to communicate via the hub, there must be an intermediate routing device. Peering by itself is not enough.
Absolutely essential. VNet peering provides the highway. The firewall provides the interchange you need for that cross-spoke traffic.
Now, what about at a massive scale?
At a huge scale, you might also look at services like Azure Virtual WAN or Azure RIDS Server. They're specifically designed to manage this transitivity automatically, so you can bypass the need for manual UDR configuration on every single spoke.
Let's turn to scenario 2, which combines peering and routing, and it leads to a surprising failure. So VNets A and B are peered and communicating just fine. Then we deploy an Azure firewall to VNet A, add a UDR to VNet A's subnets, forcing all traffic to the firewall, and suddenly VNet A can't talk to VNet B anymore. What specific setting did that UDR modification just break?
This is a consequence of introducing a routing hop. Before the UDR, VNet A's traffic going to VNet B was just following the direct system route created by the peering connection. It was simple. But by adding a UDR that sends all traffic to the firewall first, we've converted that traffic into forwarded traffic.
And what is the default security stance of Azure peering when it comes to forwarded traffic?
The peering link configuration, by default, is set to deny forwarded traffic. This is a critical security control. Azure assumes that if traffic is being routed through an intermediary device, it might be coming from an unauthorized source.
So the system route disappears, the traffic goes to the firewall, and the peering link itself blocks it.
It blocks it because it recognizes it as traffic that originated from a forwarding device, not directly from the host VM's NIC.
So the fix is structural. You have to modify the peering link settings themselves.
Correct. You have to go into the VNet peering configuration between VNet A and VNet B and explicitly check the option to allow forwarded traffic. Without that flag, the firewall cannot route VNet I's traffic across the peering link to VNet B. It's a dead end.
There's an important architectural detail here, too, about where we apply that traffic-forcing UDR. If we apply a broad 0.0.00 UDR to every subnet in VNet A,
You're forcing all traffic, internal and external, through the firewall.
which seems like overkill.
And it often is. It can introduce unnecessary latency for local traffic. The more refined architectural approach is to apply that broad firewall forcing UDR only to the outbound subnets or specific workload subnets that really require that level of inspection.
So you can exempt other subnets.
Right. Subnets that just contain PES endpoints or need minimal outbound access can often be exempted. That reduces unnecessary load on the firewall and maintains direct system routes for local VNet traffic where possible.
This highlights a crucial lesson. The moment you introduce a UDR, you are actively choosing to override Azure's optimized default system routes. You are assuming full responsibility for defining the entire path.
And you have to make sure every single component, including the peering link, supports that new manipulated path.
Building on that, let's dedicate this next section to the absolute, unwavering rules of routing precedence in Azure. This is where a lot of traditional networking assumptions really break down.
This is one of the most important concepts to master.
So Scenario 13 defines the route precedence fundamentals. If a packet leaves a VM and there are multiple potential routes, it could take a system route from peering, a BGP route from a gateway, and a user-defined route. What's the non-negotiable hierarchy?
The order is fixed, and it's critical for the exam. Number 1, user-defined routes, UDRs. Number 2, border gateway protocol, BGP routes. And dead last, number 3, system routes.
Now let's inject some friction here. The core assumption in traditional networking is that the most specific route wins, the longest prefix match.
Yep.
So a system route for 10.0.0.024 is way more specific than a general UDR pointing 0.0.000 to a firewall. Why does Azure ignore this specificity rule when comparing UDRs to system routes?
Because Azure applies specificity only within a specific category. It first looks at all the UDRs applied to the subnet and applies the longest prefix match among them. If no UDR matches, it then moves on to BGP routes and applies the longest prefix match there. It only checks the system routes as the absolute last resort.
So the existence of any applicable UDR, no matter its CIDR size, elevates it above the entire category of system routes.
Exactly. The administrator's intent, as you've expressed it in the UDR, is granted the highest priority. That broad 0.0.0.0.00 UDR is evaluated and executed before Azure even considers the internal system route for, say, VNet peering.
That is the counterintuitive part that you really have to internalize.
It is.
This reliance on UDRs as the overriding authority seems like it would introduce a massive governance challenge. How do you prevent teams from injecting conflicting or dangerous routes?
This is where governance through Azure policy becomes absolutely essential. In large organizations, you should deploy policies that audit or even explicitly restrict the creation or modification of route tables on critical subnets.
So you centralize that control.
Exactly. If teams need to introduce specific routing, that process has to be controlled. If you don't enforce this, you end up with completely unpredictable routing behavior.
Now let's see, this hierarchy created catastrophic failure. Scenario 6. Forced tunneling in Azure Service Access. We implement the classic forced tunneling technique, adding a 0.0.00 UDR to send all internet-bound traffic to an on-prem location or a central Azure firewall. And suddenly, the VMs lose access to Azure services like storage, Key Vault, and Azure Active Directory. What just happened?
The 0.0.0.00 UDR is the nuclear option. As we just established, this UDR overrides the optimized system routes that Azure uses to direct service traffic internally within the Microsoft backbone.
So when the VM tries to reach the public endpoint of Azure storage,
that traffic matches the 0.0.0.000 UDR, which forces it to the specified next hop your firewall.
But why doesn't the firewall receiving the traffic just fix the problem and route it correctly?
Because the destination IP belongs to Azure's public IP space, and the firewall might not know the optimized route back into the Microsoft backbone for those services. Or, more simply, the destination service endpoint might just reject the traffic because it's coming from an IP that has been source network address translated or SNADed by the firewall.
Instead of coming directly from the VNet.
Right. The forced tunnel basically yanks the traffic out of the protected managed Azure path and shoves it into the generic internet traffic flow, which the system services were not designed to handle.
Okay, so what are the two primary architecturally correct solutions to exempt Azure service traffic from that forced tunnel?
The first and often the simplest solution is to create specific UDR exceptions using service tags.
Okay.
You create that 0.0.0.00 UDR pointing to the firewall, but then you create more specific UDRs for destinations like the Azure Cloud or storage service tags, and you set their next hop to internet.
So you're telling Azure, for these specific Microsoft ranges, go back to using the optimized system route,
Exactly. And the second solution ties right back to our first section on endpoints.
which would be.
Use private endpoints. If you configure private endpoints for storage and key vault, the traffic never even tries to reach the public service IP. It stays entirely within your VNet using private IPs, which means it never matches the 0.0.00 route in the first place.
So it elegantly and securely solves the problem.
For highly sensitive systems, combining private endpoints with forced tunneling is the standard architecture.
Moving now to scenario 15, we're shifting focus from inbound routing to outbound identity. We have a VM with a public IP attached directly to its NIC, but when the application makes an external connection, the logs show the outbound traffic is using a different public IP address.
Yeah, this one confuses a lot of people. It's a misunderstanding of the purpose of that NIC-attached public IP. That IP is primarily guaranteed for inbound connectivity, allowing users or external services to reach the VM.
But not for outbound.
For outbound connections, Azure uses a pool of ephemeral IPs managed by the platform for SNAP.
So unless you configure it otherwise, VMs are just sharing an unpredictable pool of SNAT IPs for outbound connections.
That's the default behavior. And if your application needs a fixed, deterministic, and highly available outbound IP address, maybe to meet a partner's security requirement to whitelist a specific range relying on that NIC-attached IP is just not going to work.
What is the modern, scalable solution to guarantee a fixed outbound IP address then?
The architectural preference is the NAT gateway. It's a specialized service designed specifically to provide managed SNAT for outbound traffic. You deploy the NAT gateway, attach a fixed public IP or a public IP prefix to it, and then you associate it with the subnets that need that fixed identity,
And all outbound traffic from that subnet will then use the IP addresses on the NAT gateway.
providing both determinism and massive scalability.
It's important to remember that using an Azure firewall in a hub VNet also provides a deterministic outbound IP, right? Since all the traffic leaves to the firewall's public IP.
That's true. But the NAT gateway is the cleaner solution if the only requirement is a fixed outbound IP and scale without needing firewall inspection. It's the dedicated answer for solving outbound identity and scale problems.
You know, network problems 9 times out of 10 are actually DNS problems. So let's look at how Azure handles name resolution, starting with scenario 5, internal resolution failure. This happens because teams are trying to use Azure DNS for VNet internal service names.
The failure here really stems from confusing the scope of the services. Azure DNS, the global service you use to manage DNS records for your public domains like company.com, is public only. It has no visibility into or integration with the private address space of your VNet.
So if Azure DNS is public, what's the prerequisite service for VNet scoped internal name resolution?
You must use private DNS zones. This is a specific Azure service designed to host DNS records just for your private environment. You create a private zone, say app.internal.company.com --, and the critical administrative step is to explicitly link that private DNS zone to the specific VNet or VNets that need to resolve those names.
That linkage is the key. Without it, the internal DNS resolver used by the VMs doesn't even know the private DNS zone exists.
And it just tries to resolve the name publicly, which of course fails for an internal application record.
And this becomes especially important when you're deploying private endpoints.
Absolutely. The private DNS zone structure, often with the private link prefix, is mandatory to override that public DNS resolution.
Now let's complicate this with hybrid networking in scenario 8, hybrid DNS confusion. A site-to-site VPN tunnel is successfully established. Routing by IP address between the on-prem data center and Azure works fine.
Right.
But the on-prem servers cannot resolve Azure VM host names or private service names.
The assumption that IP connectivity equals DNS integration is the trap. The VPN only handles layer 3 IP traffic. It does absolutely nothing for name resolution. Your on-prem DNS servers are authoritative for your on-prem domain, and they have no record of the Azure VM host names or those private zones we just created.
So what is the explicit configuration required on the on-prem side to bridge this DNS gap?
You need to configure conditional forwarders on your on-premise DNS servers.
A conditional forwarder.
Yeah, it's a targeted instruction. It says, If you receive a query for any domain name ending in the Azure private suffix, like privatelink.vaultcore.windows.net, do not query the public internet or your local records. Instead, forward that query unconditionally to the specific IP address of the Azure DNS resolver or to a custom DNS server you've deployed in Azure for this task.
So the DNS traffic itself travels through the existing VPN tunnel, but only because we explicitly configured the on-prem server to point it there.
Correct. The on-prem domain needs to trust or defer to Azure's resolver for the specific zones it hosts. Connectivity and name resolution are two distinct problems that have to be solved independently in any hybrid scenario.
Okay, we've reached our final section. This is focused on scaling, application delivery, and maximizing network performance. We start with scenario 11, which tests the fundamental choice between the application gateway and the load balancer.
Right.
When should an architect choose one over the other?
The distinction is purely about the layer of operation. If your requirement is simple, high-performance distribution of traffic based solely on IP and port, that's layer 4, the transport layer, the Azure load balancer is the right choice. It's protocol agnostic, it's fast, and it handles TCP/UDP traffic with great efficiency.
But the moment we introduce application-level requirements, the choice shifts.
Yes. If the requirements involve handling HTTP or HTTPS traffic, needing URL-based routing like sending traffic for images to one pool and API to another, or requiring a web application firewall or WF, you have to use the application gateway.
And what about SSL termination?
That too. If you need to perform SSL TLS termination and offloading, has to be the application gateway.
Why can't the load balancer inspect headers or URLs?
Because the load balancer operates at layer 4. The data packet it sees is just source IP, destination IP, source port, and destination port. It doesn't look at the payload, the HTTP header, or the path being requested.
Whereas the app gateway is layer 7.
Exactly. It's at the application layer, which means it fully reconstructs the HTTP request. That allows it to inspect headers, cookies, URLs, and perform all those application-specific routing and security tasks. That layer 7 intelligence is the defining factor.
Okay, let's discuss a common operational failure point. Scenario 7, the NSG health probe trap. We have an application cluster behind a load balancer. The app is running, the local port is open, but the load balancer persistently marks the backend VMs as unhealthy.
The health check. This is failing because of the single most common omission in load balancer setup, forgetting the source identity of the probe itself. The load balancer health probes do not originate from your VNet.
Where do they come from?
They come from the specialized internal Azure management infrastructure, which is represented by the Azure Load Balancer service tag.
So if the NSG is set up to only allow traffic from my VNet subnets, what happens to that probe traffic?
It gets blocked instantly. The NSG doesn't recognize the source IP as belonging to an allowed VNet or the internet, so the default deny rules just block the probe even if the application is perfectly healthy.
And the solution is straightforward but mandatory.
You bet. The NSG applied to the back-end VMs or their subnet must include an explicit, high-priority inbound rule that allows traffic from the Azure Load Balancer service tag on the specific probe port you defined. If that rule is missing, the health check fails, and the VM is taken out of the load balancing rotation.
Okay, let's address a high-scale application headache. Scenario 9, intermittent outbound failures due to SNAT exhaustion. This symptom typically appears in applications that make a huge volume of concurrent connections to external services, like third-party APIs or external databases.
Source network address translation exhaustion, SNAT exhaustion. It's a capacity problem. Every outbound connection requires a unique SNAT port on the public IP address being used. Azure assigns a limited number of SNAT ports per public IP.
And in a high-scale environment.
In a high-scale environment, think thousands of concurrent connections. If multiple VMs are all sharing a default ephemeral public IP, they just quickly consume all the available ports. When that pool is exhausted, new connections simply fail.
And that leads to those intermittent, hard-to-debug failures.
Exactly. And just scaling out the VMs doesn't help if they all have to share the same limited IP pool.
We've already introduced the solution, but let's reinforce why the NAT gateway is the definitive answer for this problem.
The NAT gateway is purpose-built to eliminate SNAT exhaustion. When you attach a dedicated public IP prefix, which is a whole range of fixed public IPs, to the NAT gateway, you gain a massive pool of dedicated SNAT ports, up to 64,000 unique ports per public IP in that prefix.
Which provides unparalleled scalability.
Right. And as we discussed in Scenario 15, the NAT gateway also guarantees that the outbound IP is fixed and deterministic. So it solves both the scale issue and the identity issue at the same time. For any high-throughput scenario, the NAT gateway is almost a mandatory component.
Finally, let's look at scenario 14, focusing on pure network performance. We have high throughput, VM to VM traffic, but the latency remains stubbornly high. We've checked the NSGs, we've checked the route tables. What's the fundamental platform feature that's designed to address latency and maximize throughput?
The feature is accelerated networking. Modern networking platforms often use software switching layers on the host operating system to manage traffic. Accelerated networking essentially allows the VM's network interface card to bypass that software layer and go directly to the host's hardware switching infrastructure.
A technology known as SRIOV?
Single root I/O virtualization, yes.
What's the direct benefit of bypassing that host software layer?
The key benefits are drastically lower latency, reduced jitter, and much higher overall throughput. This feature is vital for things like database clusters, high-frequency trading platforms, or any application where, microseconds really matter.
And what's the critical configuration step that administrators often miss?
While it does require supported VM sizes and OS images, it has to be explicitly enabled on the NIC. The most common oversight is just assuming that selecting a high-performance VM size automatically enables it. It does not.
How do you turn it on?
To activate it, you usually have to explicitly configure the NIC setting, which often requires stopping and restarting the virtual machine to apply that hardware change. When you're troubleshooting latency, accelerated networking is the first architectural feature to verify.
That was a really comprehensive tour through the most common architectural missteps and pitfalls in Azure networking. By focusing on that common wrong assumption, we hope these concepts are now firmly rooted for you. Let's quickly summarize the four most critical, counterintuitive rules that trip up even experienced admins.
First, when you're faced with a zero-trust mandate demanding total isolation, you have to remember that private endpoints are the solution. They use private IPs inside your VNet and completely remove the public service surface. Service endpoints don't do that.
Second, the law of routing precedence. User-defined routes override everything else. That includes system routes that manage peering or internal service access. If you implement forced tunneling with a 0.0.000 UDR, you must use service tag exceptions or private endpoints to maintain access to core Azure services.
Third, concerning architecture. VNet peering is non-transitive. If you need traffic to flow between spoke A and spoke B through a hub, you must introduce a layer 3 routing device like an Azure firewall, and critically, ensure the peering link is configured to allow forwarded traffic.
And finally, scale and identity for outbound traffic. If you need a fixed, deterministic public IP address or you're seeing intermittent failures from SNAT exhaustion, the dedicated solution for high-scale environments is the NAT gateway.
The success of your Azure networking deployment and your success on the AZ-104 exam, it all hinges not just on memorizing these components, but on understanding these critical interaction points, where a UDR breaks a system route or how a simple NSG rule blocks a health probe. That's the difference between configuration and architecture.
Now, for our final provocative thought for you, the listener. We covered 15 scenarios, and each one required a specific architectural choice. We challenge you to now build, mentally, a comprehensive networking decision tree based on these traps. For any given requirement, say, must access a service over a fixed IP with WAF protection, what components does that immediately require? Application gateway, NAT gateway, private endpoint, peering. Turning these 15 solve traps into a cohesive, applied architectural reasoning process is how you will truly master Azure networking.
That intellectual exercise is the final step in moving from just knowledge consumption to confident deployment.
That concludes this deep dive into Azure networking foundations. We'll catch you next time.